Thank you, Amit. Yeah, so as Amit says, it's going to be a talk about attacks on multilinear maps and defenses, and also what we can do even if these attacks are around. So I want to say up front, this is going to be a fairly technical talk, in spite of Hugo's request that we be as conceptual as possible. There's going to be a lot of technical details, and I hope that by the end of it, many people understand a lot of the details about how these attacks work, and Mehdi will tell you about how we can modify the multilinear maps to defend against them. But so since it's going to be technical, if there's any questions at any point, please interrupt me. I want to make sure that people are following. Okay, so let's get started. So I just want to refresh. Amit mentioned in his talk what are multilinear maps, but let me just refresh your memory, or for those who weren't here. So if you recall, a bilinear map is defined on a pair of groups, G1 and G2. And it has the property that if you have a generator in G1 raised to the power A and a generator in G1 raised to the power B, and you apply the multilinear map, it moves you into the second group, G2, but multiplies the exponents. Okay, so if you multiplied these two elements in G1, the exponents would add, and the multilinear map allows you to compute products of exponents by moving into the second group. Multilinear maps are just a generalization of this to k-wave functions. So now you can think of it as having k groups, and the map would operate on inputs of length k instead of length 2. So multilinear maps have tons of cryptographic applications. A sort of canonical, easy one to see is a k+1 way Diffie-Hellman key exchange. So with bilinear maps, you can do 3-way Diffie-Hellman key exchange, and so on. And the current candidate constructions we have actually realize a noisy version of this, so where there's some additional randomness in the maps. And these things are usually called graded encoding schemes. And I'm going to talk about these now and explain what they are. It's a slightly different way of presenting them, which I think is more useful for how these are used and also how they're attacked. Okay, so in a graded encoding scheme, we have some plain text elements, which I can call M. And these are going to be encoded with some encoding E. And each encoding is going to be at some level, I. Okay, and so in notation, I'm going to say that E is an encoding of M at level I with these square brackets with the I denoting the level. Okay, so what can you do with these encodings? So let's say we have 3 encodings, E1 through E3, where E1 and E2 are at the same level I, and E3 is at some other level J. Okay, so what can you do with these encodings? Well, you can add them if they're at the same level. So I can add E1 and E2, and this produces an encoding of M1 plus M2 at the same level I. And I can also multiply across different levels. So if I can multiply E1 and E3, and this would give me an encoding of the product M1 times M3, and now at level I plus J, where E1 was at level I and E3 was at level J. Okay, and then the final thing I can do is zero test. So given an encoding, I can check if it's equal to 0, if it's an encoding of 0. But there's a crucial caveat, which is I can only perform the zero test if I'm at the top level k. So there's some maximum level k, and the zero test will only give me a meaningful answer if the encoding is at the top level k. And specifically, it will tell me whether or not it's an encoding of 0. Okay, so I think it's useful to think about these graded encoding schemes in contrast to fully homomorphic encryption. Okay, so in both graded encoding schemes and fully homomorphic encryption, you do these arithmetic operations on encoded values themselves. Okay, so I don't need to decrypt to do the arithmetic. I can just do it on the encoded values themselves. But there's some crucial differences. So in a graded encoding scheme, when I decrypt, so think of decrypt as the zero test, I only decrypt to get 0 or 1. So in particular, I don't learn the actual value of the encoding unless it's 0. I just learn if it's 0 or not. In contrast, in FHE, when you decrypt something, you get the actual value that was encoded. Okay, and another key difference is that for graded encoding schemes, you can only decrypt at the end of the computation in some sense, when you've reached maximum level. And in contrast, in FHE, you can always decrypt. There's no notion of levels in this way. Okay, and the reason why I'm sort of pointing out these differences is because I think this illustrates why graded encoding schemes are kind of naturally suited to do program obfuscation. Right? So what you want to do is give out some encoded inputs, allow people to do computation on them, and then at the end sort of decrypt and see the result. And let's say it's a Boolean function, so the result is 0 or 1. So with FHE, you can do these things, but you can also do more, which we don't want for obfuscation, right? You can also decrypt the intermediate values, which we don't want. Yeah?
But in FHE, you need a key to decrypt, right?
Sure, that's true. That's another good point. So you can think of, so for the zero test, there's going to be a sort of key. There's going to be a parameter that lets you decrypt. It's not like if I have an encoding of 0, I can just look at it and see. There is a key that is going to be used to sort of get the answer. It's sort of a, yeah, you can think of it as a like defective FHE key. So instead of letting you decrypt, it just lets you see if it was 0 or not. It's public, yeah, it's public. Yeah. Okay. So let me briefly now go through the history of graded encoding schemes candidates from the last about 2.5 years. So the first breakthrough one of these was due to Garg, Gentry, and Halevi at the end of 2012. This is a candidate based on ideal lattices. Okay, and pretty quickly after, the same authors noticed that there was something called a zeroizing attack on this candidate, which essentially means if I have some low-level encodings of 0 in some specific form, I can actually attack the scheme and break the security in some sense. I'm going to be informal here on this slide. Okay, in 2013, there was another candidate due to Caron, Lapointe, and Tabucci. And this is a candidate over the integers, which uses Chinese remainder theorem representation. Okay, last year there was another candidate, GGH, but this is a different GGH. This is Gorbanov, Gentry, and Halevi. And this is yet another candidate that has a different form than the previous two, and in particular, it kind of has a more LWE-like form than the previous ones do. Okay. Late last year, there were some attacks on the CLT candidate, and in particular, Qian, Han, Li, Ryu, and Stelly gave a zeroizing attack on CLT. So, like the zeroizing attack on GGH, this attack relied on low-level encodings of 0. And then this was quickly extended in joint work with Caron, Gentry, Halevi, Lapointe, Maggi, Raikova, Sahai, Tabucci. So this extended the attack of Qian et al. To different settings, and in particular to settings where we don't assume there's any low-level encodings of 0. So this is really like a conceptual contrast to the previous attacks. Up until this point, all known attacks on M-maps required low-level encodings of 0, and now for the first time we can start to see that there's attacks even when these are not present. Okay, so earlier this year there was a new version of CLT by the same authors, which modified the original one to sort of resist these zeroizing attacks. And then, even more recently than that, there was a new attack on GGH 13. And this is not really a zeroizing attack, but this attacks a sort of a key exchange protocol using those encodings. So this list actually keeps going on. I ran out of room on the slide, but you can see that this is like very active area, lots of back and forth, as Amit said. And the reason for this, why everybody is so interested in these things, is because they have an amazing number of applications. So, obfuscation is sort of the gold standard application, but there's many other applications like witness encryption, functional encryption, and many other things. I'm not going to get into the motivation about or applications of these M-maps, but they are numerous. And instead, I just want to talk about how the M-maps work and how we attack them and how we can hope to prevent these attacks. Okay, so And in particular today, the talk is going to be about the CLT family of M maps. Okay, so we're going to talk about the CLT M map itself, the zeroizing attacks from last year, and then Mehdi is going to talk about the new version of CLT, which seeks to defend against these attacks. Okay, and in particular, I'm not going to cover many things such as the original zeroizing attacks on GGH13. I'm not going to talk about what's known about the cryptanalysis of GGH14. There's also an extension of the attacks. This is in our upcoming crypto paper. An extension of the Chiana et al. Attacks to GGH13, which actually doesn't rely on low-level zeros either. I'm not going to talk about those. And these recent attacks on GGH13, including this one by Hu and Jia, and more recent ones, I'm not going to talk about these either. So this is really going to be focused on the CLT family of M maps. Okay. So here's the plan for the rest of the talk. First, going to give an overview of the CLT13 candidate itself and how it works, and then talk about the zeroizing attacks on it. And then Mehdi is going to talk about the new candidate, CLT15. And then at the end, depending on if there's time, I'm going to say a little about what we can hope to do even if these attacks are inherent. Even if we can never eliminate zeroizing attacks, what can we still hope to do?
Okay, sorry, I'm
Yeah.
confused. What are you saying? Is there a candidate based on ideal lattices that stands at this point, or is it only this candidate stands?
No, good. Okay, so there's an attack on the GGH13 candidate if you have encodings of 0 of a certain form. Oh, sorry. Yes, without low-level zeros. Okay, that's true. They're sort of, you're not directly given low-level zeros. You're given matrices of GGH encodings in a form where there are low-level zeros, but they're not directly given out. So yeah, I don't want to emphasize this too much because this is not an attack directly on the GGH scheme, and it doesn't break anything, any application that we know of. But there's an interesting observation that this can extend even to this setting.
And the CLT15, there's no attack, right?
Not to my knowledge. Maybe no, I don't. Not yet. Hopefully not ever. Okay.
But also, the latest attack, Shafi, the attack on the MPKE protocol, that also uses low-level encodings of 0. So with regard to GGH13, there just are one little example of an attack without low-level encodings.
Yeah. Yeah.
Are you saying that all the schemes that Amit just discussed would still work with either GGH or CLT13 or CLT15?
Well, okay. So one thing is if the scheme requires composite order maps, then you cannot use GGH13 because this is prime order. But other than that, yes, the answer is yes. So in particular, all of the obfuscation schemes are not broken by these attacks. And the reason is that the encodings given out there do not have the form that is necessary to apply the attacks. Yeah, I'll come back to that. But yeah, I want to emphasize this like several times throughout the talk. None of the NC1 obfuscation candidates are broken by any of these attacks because the encodings do not have the correct form. There's some simplified variants of these schemes which we can break, but none of the ones as they're published are broken.
But there are some schemes for which the assumption presented is false.
True.
In particular, the only scheme for which the assumption is not yet false is CLT15.
Yes.
Yes, that's true. Correct. Yeah. But that doesn't mean that the schemes themselves are broken. Okay. Okay. So let me get into the details of how CLT13 works. Okay. So CLT13 has some system parameters. It has two sets of primes. The P primes and the G primes. And the P's are going to be much bigger than the G's. Okay, and then it has this value Z, which is going to be used to sort of encode the level of the encoding. Okay, and so the primes and this level value Z are secret. And there's a public parameter, which is modulus. So this is going to be denoted x0, and it's the product of all of the large primes, the p primes. Okay, plain texts in the CLT scheme are vectors, vectors over z to the g1 through z to the gn. So it's a vector where the ith component is some number modulo gi, modulo the small prime.
So everything short.
Yeah, the plain texts are short relative to the modulus in particular. And so the encodings are going to live in z to the x0, so this is modulo the modulus x0, and the encodings are going to be done via the Chinese remainder theorem. Okay, so this is just overview of what things are going to look like, what things we're going to be using. Okay, so how do we encode? So let's say we have some plain text vector, m1 through mn, and we want to encode at level j. Okay, so the encoding looks like the following. First we have the level value. So we have z raised to the minus j. So j is the level we want to encode at. And we're going to multiply this with the CRT representation of this vector e1 through en defined as follows. So ei is the message, or the message vector, or the message slot, mi, plus some randomness, which is divisible by the prime gi.
So I already forgot what z was. Sorry.
Good. Z is just going to be used to sort of encode what level you're at. And this is actually going to be the least important thing. In all of the attacks, these z's are just going to kind of go away. So you can safely ignore them if there's too much notation on the slides. Okay, so again we have this level value z raised to the level we want to encode at, minus j, multiplied by the CRT representation. Okay, and notice that in each component of the CRT representation, if I take that component ei, mod the corresponding prime gi, so remember this is the small prime, I get back the message bit. So these components encode the message values mod gi in some sense.
So mi is super short and ei is short. Just something, right?
Yeah.
Like 3 level short. Okay.
Yeah. Mi is very short. Ei is short, but it's of course larger than mi. But and the GIs are very short, and the randomness also is very short. So most things are very short. What's not short is this value z to the minus j. So this is large. So in particular, an encoding will not look like a small value in this ring. Okay. So this is the kind of invariant that we want to maintain in these encodings. And we're going to do arithmetic on the encodings, just mod x0. So an encoding is an integer, mod x0, and we do arithmetic on them, mod x0. Okay? And as long as you're following the rules of the arithmetic I had on the second slide, so you only add at the same level, and when you multiply the levels, the level numbers add, this invariant will be maintained as long as the number of operations doesn't get too large. So as long as you do some bounded polynomial number of operations, which is determined by the parameters of the scheme, this invariant will be maintained, and the encodings will still have the proper form. Okay. So now let's see how zero test works. Okay, so for notation, I want to define this value pi star, which is which is the product of all the primes except the ith. Okay, so it's a product of the primes pj as long as j not equal to I. Okay, so with this notation, the zero test parameter looks like the following. It's a CRT, it's a Chinese remainder theorem representation of some vector, which I'll explain, multiplied by a level value. So there's a couple things to note here. So first of all, the level that we're multiplying it by is k. So the zero test parameter has this z to the k, which sort of corresponds to that you should only be able to apply the zero test at the top level. So k here is the top level. Okay, and then what are the components of the CRT look like? Well, each one has this P1 star, Pi star, which is the product of all the primes except the ith. And then it has some randomness, H, and the small prime G inverse. I know this probably looks like a big mess right now. On the next slide, you're going to see how the zero test works, and these things will, the reason for these things will become clear. For now, I just want to say that these Pi stars have this property that if you want to compute the CRT representation of a vector where the ith slot is divisible by Pi star, then the CRT representation is just the sum of the elements mod x0. Okay, so this is going to be useful, and this essentially follows from the Chinese remainder theorem, or you can see it as a component in the proof. Okay, so to clear things up a little bit, let's see how a zero test works. Let's see how a successful zero test works. Okay, so let's say I have some encoding, let's call it A, at the top level K. So what this means is that the encoding A is of the form z to the minus k, representing the level, multiplied by CRT, where the ith component of that CRT is the plaintext message, plus some randomness, which is divisible by the ith prime g. Okay? And then the zero test parameter has a similar form. So it has this level component, z to the k, and it's a CRT of some stuff that I described on the last slide. Okay, so to do the zero test, you take your encoding, you take your zero test parameter, and you multiply them, and that's it. Then you're gonna check if this value is small or not. But the operation of doing zero test is just multiplying these two things. Okay, so what's going to happen when you multiply them? Right, these are going to cancel. So you're just left with the CRTs. And now, if A is an encoding of 0, what that means is that all of these MIs are 0. So the MIs are gone. Okay? And when you multiply two CRTs, they multiply component-wise. So if the MIs are gone, then this GI will cancel with this GI inverse. Okay? So that's essentially what this says. So if all of the message slots are 0, you do the zero test by multiplying the encoding and the zero test parameter. And what you get is just a CRT vector, a CRT representation of this. So this is this Pi star, this randomness H from the zero test parameter, and the randomness R from the encoding. Okay, and the crucial thing here is that these are all small. Okay, so HI and RI were both chosen to be much smaller than the prime PI. And this is the product of all the primes except the ith. And so in particular, each one of these is much smaller than x0. Recall that x0 is the product of all the primes. Okay, so and again, because the CRT representation has this form where each slot is divisible by this Pi star, the CRT is equivalent to just summing these elements. Okay, and because all of these things are small, the sum is going to be much smaller than x0. And this is how you recognize a successful zero test. So if when you multiply the encoding and the zero test parameter, you have something that's much smaller than x0, then this tells you that your encoding was an encoding of 0 at the top level k. And if not, so if there's some message slot which is not equal to 0, or the level is not equal to k, things will not simplify like this, and you will have some big values that are big relative to x0, and so you will get a number which is roughly x0. Okay. So this equation, right? What happens with a successful zero test? This is essentially the simplicity of this equation is what allows the zeroizing attacks to work. So in particular, I want to note a couple of things. One is that this equality holds over the integers, so without modular reduction. meaning that if you take your encoding and your zero test parameter, you multiply them and reduce mod x0, so you have some value. This is equal to this sum, and it's not just equal to it mod x0, it's actually equal to it. Okay? And then the other thing, which I'll note here, but this will come back when we're going through the attacks, is that this sum actually has a kind of simpler form, which is that it's just the sum of the RIs, which came from the encoding A, but then these RIs are multiplied by some other things that don't depend at all on the encoding. Okay, so these are just system parameters. These PI stars and the HI are all system parameters. So when you do a successful zero test, you wind up with a sum of something that depends on the encoding times some stuff that has nothing to do with the encoding. Okay. Yeah.
What happens if you use this as a bilinear?
What do you mean?
I mean, 2 levels.
2 levels. Okay.
Do you get something intuitive, something?
So, I mean, 2 levels would correspond to k equal to 2. So, actually, I'll tell you what. When I go through the attacks, it's going to be a very toy example. So it's just going to be 2 primes and 3 levels. So maybe it'll be more clear. Okay. Any other questions at this point? Yeah.
If x0 is not a composite number, but you just take one slot, would it be obviously broken?
Yeah, I believe this this should be easily broken. I'm not sure exactly what the form is, but so if you have the primes pi, and in particular if there's only one and you know it, you can recover all of the other system parameters. I'm not going to go into the details of that, but knowing the primes is a break on this thing. So in particular, if you can factor x0, you break the security of the scheme. Yeah.
What about the GIs?
The GIs. So the GIs, I believe you can recover the GIs with essentially if you have enough encodings, you can do GCDs to eliminate these things. So if you have enough encodings of 0 and you know all the primes pi, are you asking if you just know the primes GI? I'm not sure. Okay, Mehdi says we don't know of an attack if you just know the GIs. So.
But it's still secret.
It's still secret. Yeah. Yes.
But the HIs, what are they doing there? Why can't they just be 1?
Right. I mean, so for the purposes of this, they can be. I mean, they wouldn't affect the correctness. Maybe Mehdi can say something about why you decided the HIs. I think my impression is just more randomness. Is better, but you're right. Like not everything on this slide would.
You could square the zero test parameter and check to 0 at level 2k, and that would be bad. I mean, it's something that's not too small so that you can't square it and still.
No, but the GIs would square then too, no?
So you test. Well, then you need more you need to multiply more zeros.
Okay.
You can multiply it with 1 0 encoding, and the zero test will get rid of one of the G.
Yeah, I see. Okay. Any other questions? Okay. So now let's see how some of the zeroizing attacks work. Okay, and I'm gonna start by presenting the attack by Qian et al. Okay, so I'm gonna show this as a kind of in a toy version of this, where the number of primes is just 2, and the top level is 3. So there's 2 slots in each CRT, and you need to multiply like 3 encodings to get to the top level. Okay, so this attack is going to assume that you have 3 sets of encodings, which I'm going to call an A set, a B set, and a C set. Okay, so the A set looks like this. This is just notation. So all these encodings are at level 1. And this is just to remind you that an encoding A is a CRT of some numbers multiplied by z to the minus 1, or divided by z. Okay? And then the B set and the C set are the same. This is just notation to remind you of what the encodings look like. Okay, so you'll notice that all these sets have size 2, but this is because this is a kind of toy example. So in particular, when you do the attack for real, the A and the C sets have size n. So you need one encoding in each of these sets for each prime that there is. But here we just have 2 primes, so there's just 2 encodings in each set. Okay, and then the middle set, B, there's always 2 encodings. So regardless of how many primes you have, this middle set is always just going to have 2 encodings. And in some sense, you can think of these middle encodings as the target of the attack. So what the attack is going to recover are essentially going to be these CRT values in here. Okay, so we're going to use the A and the C sets to recover the sort of hidden values in these encodings here. Okay? So, unsurprisingly, we cannot just take any sets of encodings. We need these to have some special properties. And in the Chian et al. Attack, what they require is that the A sets are all encodings of 0. Okay, so each AI is an encoding of 0. And recall that this means that so for example, if A1 is an encoding of 0, it means that each slot in the CRT representation is divisible by the corresponding G prime, right? Because they had the form like G times some randomness plus the encoded value in that slot. So if the encoded values are all 0, then each of the CRT values are divisible by G, by the corresponding GI. Okay? So it was observed by us and also by Bonnet, Wu, and Zimmerman that in fact this assumption is not necessary for this attack. So we do not need to assume that the AIs encode 0. And it's sufficient instead that the following is true. For any way of choosing one encoding from the first set, one from the second, and one from the third, for any way of choosing those, the product is 0 at the top level. Okay, so it's enough to satisfy that if the AIs encode 0, but you could imagine other forms where, for example, the AIs might have 0s in the first slot, and the CIs have 0s in the second slot. Okay, so then none of these are actually low-level encodings of 0, but they multiply to 0 at the top level. Okay? Okay, so given these sets of encodings, here's how the attack works. So I'm going to take one element, one encoding from each of the 3 sets and multiply it. So let's say I take the first one from A and the first one from B. Yeah, so you'll probably notice that I'm denoting the B slightly different, which will make sense in a moment. But let's say I take the first encoding from A, A1, the first encoding from B, and from the B set, and the first encoding from the C set, which is C1, and I multiply these. Okay, so I haven't done anything here except notation. So these are now encoded at level 3 because they were each encoded at level 1, and the CRT slots are just the products of the slots from each of the encodings. But here again, I'm emphasizing that this is divisible by G because it's an encoding of 0. Okay, and again, recall what the 0 test parameter looks like. It has this Z, which is going to cancel with here. And then when we multiply these two, again, these G's are going to cancel here. Okay, so let's say I do that. I take my 3 encodings that I multiplied. I multiply by the 0 test parameter. And I get something, that looks like this. So again, it's the CRT representation of these products, but because of these like PI stars, I can just add. That's what the CRT representation looks like. Okay, and now just to sort of clean up the notation a bit, I'm going to forget about what form these actually have and just call these system parameters. So these sigmas are some parameters that depend on the system and not on any of the encodings. And then the CRT components of each of the encodings are multiplied. So this is the product of all of the first CRT components, and this is the product of all the second CRT components for these encodings that I multiplied. Okay? So it has this form I'm going to call this W11, which means that I took A1 and C1. Okay, and I can, and again, this is crucial that this holds over the integer. So once I compute W11 in this way, W11 is equal to this sum over the integer. So no modular reduction is needed in that equation. Okay, and this is crucial for this attack.
And these A's, B's, and C's are small.
These are small, yes. And that's why this holds over the integers, because everything here is small. Exactly. Even these system parameters are small relative to x0. Okay. So I can write this sum in matrix vector form, right? Because it's just a bilinear form in some sense, right? So I have this vector of the AI CRT, the A1 CRT components. Over here I have the C1 CRT components. Okay, and then in the middle I have this diagonal matrix, which on the ith diagonal has the ith CRT component from B times whatever system parameter is there for that slot. Okay, so I'm very close to the punchline for this attack. Right now I'm just setting up these matrices. Okay, so I did this for A1 and C1, and I called this W11, but I can do this for any way of choosing something from the A and something from the C. So in particular, I can make a matrix W, right, where the ijth entry of W is AI times B times Cj. Okay, and it has this form. So now let me just let me take this and move this up. Okay, so again, I have this matrix W, where the ijth entry is the zero-tested version of the ith encoding from A, this middle encoding B, and the jth encoding from C. Okay, and that matrix W has this decomposition by the properties of the zero test. Okay, let me clean this up a little bit. Let me just call the stuff on the left an A matrix. This only depended on the A encodings. And the stuff on the right, the C matrix, only depended on the C encodings. Okay, so we did this. Notice that we did this with this B in the middle. So this B was fixed in every product. Okay, I varied the A's and the C's, but I kept the B the same. Okay, now I can do the same thing, but using the other middle encoding. So remember, the B set had these two encodings, B and B prime. So I'm going to construct exactly the same matrix, but using B prime instead of B. Okay? So now we have these two matrices that have somewhat similar decompositions. And we would like to get some of these things to start canceling so that we can recover the sort of internal hidden values here. Okay, so how do we get these things to cancel? Well, instead of computing this W prime like this, I'm going to compute its inverse, actually, which I can do over the integers, over the rationals. Okay, so I won't go into the details, but with high probability, each of these W matrices are invertible. And so if I invert the second one of these, this has the effect of when you invert this matrix product, you just flip the order and invert each of the things. So now you get C minus 1 over here. Yeah.
So you don't need A and C to be invertible, right?
So what you need is that, you need these to be invertible, but these will be with high probability over the randomness of the encoding. You can essentially think about these as somewhat random numbers.
You need many independent encodings.
The encodings definitely need to be independent. The randomness needs to be independent. You need, it depends on how many primes you're working with. But yes, you need, if you have n primes, you need n A encodings and n C encodings, yeah.
For applications like key exchange, do you need that many encodings of 0? Or maybe for these applications, you just need fewer encodings of 0 and that takes you to work?
That's a good question, which I'm not sure of the answer to. For the key exchange, I don't know if you need n encodings of 0. You do, yeah, okay. Okay, so here's where we were. We have these two matrices, W and W prime. W prime is inverted. Okay, and now notice what will happen if I multiply W and W prime. Okay, what will happen is that these C's will cancel. And here, these system parameters, sigma, will cancel. Okay, so when I multiply these two things, again, over the rationals, what I'm left with is this decomposition that has A on one side and A inverse on the other. And in the middle, we have the ratios of the CRT components of the B encodings, right? So B1 was the first CRT component of B, and B1 prime is the first CRT component of B prime. Okay, so I want to emphasize here that we, the attacker, don't actually know these values. We computed W and W prime, but we know that it has this decomposition. Okay, and now let's say we want to recover the values here. Well, we can do that just with an eigenvalue computation, right? So this matrix here, it's a diagonal matrix, so these are the eigenvalues. And the matrix that we have is similar to this matrix because it's in some sense conjugated by A. And so the eigenvalues of this are the same as the eigenvalues of this. So we can recover these internal values via the eigenvalues.
But why can't you do it over Q?
This is over Q. I'm not sure. You're computing the eigenvalues over Q.
Everything was over X0, and you switched to Q.
Right. I switched to Q.
Why did you do it? Oh.
I switched to Q when I took the inverse.
Okay.
This is the inverse of an integer matrix.
Okay.
Yeah.
And that's legal.
Sure. I mean, I have. I mean, unless you're going to stop me. I mean, I have the matrix. It's an integer matrix, and it's invertible. Yeah. So I can do this. The reason why this all works out is because things are small. Because these actually held over the integers and not just mod x0. That's why it's legal. Yeah. Yeah. If these were big, then this would not work. That's why successful zero tests are kind of crucial for this attack. Okay. So again, we can recover these ratios of the CRT components by computing the eigenvalues of this matrix. And with these, you can actually factor x0 and break everything. So these are enough to sort of factor the modulus, recover the primes, and you can break everything. Good. So I was gonna not do that, but I can tell you quickly. The idea is that if I take B. So I take the encoding B, okay, and I'm going to multiply by B prime 1 by the first CRT component. And now I'm going to subtract B prime times B1. Okay, so notice I sort of switch these. These B and B prime are the actual CRT encoding. And then these are the sort of just components that I recovered.
So this is going to be a vector.
No. These are just integers. All of these things are integers. Yeah. So the point is that.
Wait, can I interrupt you? So from that ratio, you're saying you can actually recover BI and BI prime.
So you don't recover them. You recover their ratio. So they may have some factors in common. But even if they have factors in common, the following thing holds, which is that you can compute something like this. These B1 prime and B1 may be reduced by their common factor. But the point is that this is divisible by P1. Okay, and the reason is that in the first slot, it will get the value will get zeroed out, and it's just divisible by P1. Okay, and so the point then is the GCD of this and x0 will be equal to P1. Okay, so this is how you recover the primes. I want to talk about generalizations of this attack. I'm not sure how much time is left. because I want to leave Mehdi some time. 20 minutes? Okay. So actually, maybe I should just skip ahead and let Mehdi, if that's all right. Okay. Okay. So I'll just say there are some generalizations of this attack. I already mentioned when you don't have low-level zeros, when you just have things that multiply to 0 at the top level, things still work out. There's another generalization where even if you don't directly get a 0 by multiplying, but you need to sort of compute some linear equation to get the zeros. Again, this still works out. The matrices just have higher dimension. And this breaks the immunization of CLT13 proposed by Bonnet, Wu, and Zimmerman. And then even if you have more general relations amongst the encoding, so not just this sort of simple linear relation, but sort of more general linear relations that you need to get zeros, you can do something very clever with the Cayley-Hamilton theorem, which again is probably more details than I have time to go into right now. I'll just quickly say, so some consequences of these are that these attacks break simplified variants of some obfuscation schemes. So in particular, the Garg et al. Branching program obfuscation scheme and the circuit obfuscation schemes proposed by Zimmerman and Applebaum and Bukersky. So these are not broken, but simplified variants of them, very simplified variants of them, sort of trivially simplified variants of them can be broken with these attacks. Okay, but again, no candidate NC1 obfuscator is known to be broken by these attacks. Okay, so let me let Mehdi take over. Yeah.
Amit described, where in his proof he needed to zero out these.
Right. So those encodings do have the form to do this attack. So that assumption is broken over CLT13 because those zeros are in a way such that you can multiply to get top level zeros. Yeah.
So we need the new candidate.
Right.
Okay, so now that's it. Okay, so now I want to describe how we sort of try to avoid thwart the attack that Eric just described. So abstracting things a bit. So the reason why the attack works is that you have in some sense zero testing is linear. Or you can construct bilinear forms of integers. So have slightly different notations. I'm sorry. So this thing here is the result of applying zero testing to some encoding. So of 0 at the top level. So this is what Eric denoted by PZT time A mod x0 or something. And so you had some like this where, so if I denote by C the encoding question, you have a C appearing here together with things which you can use to construct the matrices that Eric described. So again, so you wrote it in terms in matrix term, and you do it twice. You divide, and you can extract information as eigenvalues. So how can you avoid this? As he said, an approach that didn't seem to work out is trying to keep the exact same number theoretic construction, but somehow use a more complex representation of the encodings so that it doesn't seem so easy to combine the encodings in such a way that they produce the zeros that you need at the top level to obtain the relations that let you let the attack work out. So, for example, you had this. He mentioned the Bonnet-Zimmermann countermeasure, where, in some sense, so encodings were represented as pairs of CLT13 encodings, and somehow, and so you could make sure that you didn't get low-level encodings of zeros, but still you can combine them so that you can get encodings of zero at the top level. And so since zero testing was basically the same, it still had this linear structure, and you still could express the zero tested value as a bilinear form, and the attack applies exactly the same, just with larger dimensional matrices. So in the last part of the talk, Eric will say things that hopefully can be done in that spirit. But we here in CLT15, we take a different approach. So the idea is that encodings themselves, in principle, they shouldn't be a problem. So essentially, encodings in CLT or in GGH, they're like FHE ciphertexts for the kind of FHE scheme that they are inspired from. So in our case, they look very much like ciphertext for FHE over the integers. So if you don't give out the PZT, the zero testing parameter, then they pretty much pseudo-random. I say almost because the shape is slightly different, but so you don't exactly get security proof, but almost. So the problem is zero testing. So the fact that zero testing is you can get those bilinear forms from zero testing. So that's we want to break. So what we try to do is keep the basic structure of CLT13, but just modify the zero testing procedure to make it nonlinear in some sense. So the way we do this is carry out zero testing with a different modulus than the modulus we use for multilinear operations. So we introduce, so encodings are still CRT values mod sum x0, but to do the zero testing, we check whether PZT times C, where PZT is a suitable value, is small modulo some independently chosen prime, which is larger than x0. So I'll describe this in more details in this part. So just to describe what CLT does in a nutshell. So we keep the same CLT encodings. So but we modify the zero testing in such a way that we think the zero tested value can't be expressed as a bilinear form anymore. So the new arithmetic technique is to map the CRT components of a given encoding to some value modulo an independent integer in such a way that you can do zero testing by testing whether things are large or small with respect to n. Okay, so so the attack by Chon et al. Doesn't seem to generalize to that setting. So you can't write, you can't construct such a matrix WC anymore. You still have a matrix representation, but it has additional terms which are nonlinear, and so when you try to divide two such matrices, you don't get anything interesting, apparently. Okay, so again, so CLT encodings over Z, they look like this. So that's exactly the same thing as Eric wrote. It's a slightly different notation. So C is the encoding, and if you reduce it mod pi, then it looks like the value mi plus some randomness that depends on that's multiplied by that's divisible by gi, divided by Z to the kappa at level kappa. Okay, so another way to write this is like this. So I just expand everything with CRT. So the CRT components are obtained with a relation of that form. So you invert the rest of the modulus, mod the pi, and you multiply by the component modulo pi, etc. So you have over Z. So once I reduce everything mod x0, I can write this relation over Z, and I get a term, an extra term here, which correspond to integer division, Euclidean division by x0. So here is just values, the CIs, the components over pi, times some constants, minus a times x0. Okay, so that's the structure. And I said that I could do zero testing modulo an independently picked random large prime n, provided that I can find an element pzt mod n, such that when I pick all of those terms and I multiply them by pzt, they become small compared to n. So why is that? Because if I can find such a pzt, then I take this relation, I multiply everything by pzt, and the ui become vi, and the x0 time multiplied by pzt it becomes v0. And so this thing, so suppose all the mis are 0, then all I get is ri times vi. Ri is very small and vi is small compared to n, and a times v0. And if all the mi are 0, then the size of a is the same as the size of the ri's, which is an important remark. And so it's also small. So everything is small if all mi's are 0, whereas if not all mi's are 0, then this thing will get larger. It's the size of p, and a will get larger as well, and this won't be small anymore. So that's the idea. So how can I find such an element pzt, which, to remind you, is such that so ui's are parameters that depends on the pi's, and so such that pzt times ui mod n is small for all ui's, and v0 is also small. So in some sense that's a lattice problem. So I want to find a small it's the same as finding a short vector in a lattice of dimension n+1, something like this. The lattice generated by the ui's and x0, and with a diagonal of n's, something. So in principle, I don't need a very small approximation factor, so I could do this with LLL. But doing LLL, so in practice, n is something like 10,000. So LLL in the lattice of dimension 10,000 is not such a good idea. So we exploit the fact that the UIs have a special form that makes our job easier. So the special form is like this, something like that. They all depend on each other very closely. They're basically multiples of CRT components. In our case, so n is a bit larger than x0, something like the size of x0 times the size of one of the pi's. And then what we claim is that if you take UI like this and you divide it by one of the primes over than pi, so if you divide it by one of the prime over than pi, then it becomes small mod n because it becomes small over the integers. Because pj for i different from j, divides x0, and so it divides ui, and so you can divide it by it mod n. So this is small. So your only problem is when the two indices are equal. And it makes your job much simpler. So
minus k is not small. So the previous slide, z to the minus k, that's a huge number. So why is it small?
Oh yeah, but all this thing is just modulo pi. So it's just the size of x0. So the only thing you need to deal with is those terms. You want to make them small. So that's doable just with LLL in dimension 2 this time. So you can find by balancing the components something which is of size root of p, something like this, such that this thing is of size at most n divided by root p, something like this. So both of those things become small. And so then all of those terms, all of those products will be small mod n. So some because they're already small and you multiply by something small, and the others because it's just beta j. And so you take a random linear combination with small parameters of those things, and you get your zero testing element, which satisfies the property that we wanted. Okay, so I will need more than 2 minutes, I think. Can you give me 5 or?
No, we're already eating into our discussion time.
5 minutes is good.
5 minutes is good. Okay.
Thank you very much. Okay, so one important thing to note is that the x0 that we considered since the beginning must be kept private in this scheme. The reason is that if you make it public, then I can do the Chern et al. Attack modulo v0 here. Eric described the Chern et al. Attack over Z or over Q, but you could carry it out in a different over a different field, and so for example, or a ring. And in this case, the ring of integers mod v0 is a perfectly fine ring to carry out the same attack. So you can do it, and it would break things. It would break everything because the zero testing parameter has exactly the same form, mod v0, as it did in this previous situation. So you must keep x0 public, and that's rather inconvenient because when you add and multiply encodings, then you can't reduce things mod x0 anymore. Which is inconvenient, and it's even more important for zero testing at the end, because remember that zero testing used the fact that your encoding was small enough such that the A term at the end, this A here, was of the same size as the arise, for example. So you need to, even though you don't have x0, you need a way to reduce the size of encodings at each step. So you can do this by publishing a ladder of random encodings of zeros and reducing bit by bit. So that's a technique that's been known forever. So in practice, it was used for the original FHE scheme of the integers by Van Dyck et al. In 2010, which is forever ago in those terms. Okay, so then the question is, so have we really stopped the attack? This relation for the description of the zero testing is not so different than CLT30, but you have this critical term A times V0, which doesn't depend linearly on the arise, and so it seems that whatever you do, you will still have this term, where A obscures everything and avoids this division trick that the Chern et al. Were able to carry out. Moreover, So, as I explained just a minute ago, you can't do zero testing directly on the product of lower level encodings. You must first reduce your product to something which is of the size of x0 before you can multiply by pzt. And this means that you have to carry out this size reduction step by adding ladders of encodings somehow. And those ladder terms also add some nonlinearity that seem to thwart the attack as well. So in the end, you will have a real zero testing term of this form, where you have two types of additional terms, the SIs which come from the ladder, and the A which comes from the Euclidean division of those things by x0. And all of those are nonlinear in the components of the CIR. And so those additional terms seem to make the attack not work. So that's of course, not a precise statement. Maybe you could somehow modify the attack to make it work, but we haven't found a way to do this. I won't talk about setting parameters, but let's just say that there's an implementation of this by Tancred Lepoint, who is here. So you can play with it if you want. And the actual parameters are not especially worse than the one in CLT13, which is not a very strong statement. Okay, that's it. You can.
I think since we're significantly over time and eating into the discussion, I don't know if you want to just say one word about the result, and then we can.
One word, okay.
Yeah.
So okay, I mean yeah, it's good. So this is the idea of post-zeroizing obfuscation: is not to allow any zero encodings at all. So never allow anyone to create a zero encoding, and none of these attacks work. So that's it, we're done. No, okay, but you need zero encodings because sometimes functions output zero. So think of it just in the case of evasive functions, so where it's hard to find a zero output. Then this makes sense, and these attacks at least are not obviously applicable.
You can obfuscate the obfuscation.
Yeah, you can do that too.
So you have a result of this case evasive function which do something else.
Yes, obfuscates evasive functions and shows that an adversary which sort of follows the rules never creates a zero encoding. So in all of these zeroizing attacks, the adversary follows the rules, right? It adds and multiplies in the way it's supposed to. Okay. So you might think that this follows from the fact that we're talking about evasive functions, but getting a function output of 0 is not the only way to get a 0. So this does require some work to prove that in addition to not being able to get 0 outputs, you can't get any zeros at all.
But if you get a collision, can't you subtract the outputs?
Yeah, but so if you get a collision of ones,
you get f of x is equal to f of x prime.
Right. What that means is that they're equal as Boolean functions, but the underlying field element is not the same. It's something random-ish that's not 0. So even if you have two outputs that are both 1, the actual field element that's encoded in each case is not the same. So when you subtract it, it will not be an encoding of 0. That's a good point, though. Okay, yeah, and so there's a sort of like key theorem which allows to prove this, which sort of shows that the types of encodings you can create in some of these obfuscation schemes is very restricted. And I think it's conceivable that you could use this theorem to prove something like that. With these obfuscation schemes, you just can't get the types of encodings you need for these zeroizing attacks. What we have is just to prove that you can't get zeros with evasive functions, but conceivably this theorem could be used to prove more than that. Okay, I'll leave the conclusion up.